two vortices thing, so it acts as a pump, similar to the slide before. But if you let the particles to be free, you don't glue them to the surface, then this mechanism leads to the motion of the particles that you have already seen. So the summary of this part of the talk is that if you compare just the simple linear electrophoresis that occurs in isotopic electrolytes to the case when you're using a liquid crystal, the simplest liquid crystal, the pneumatic phase, as an electrolyte, you see dramatic qualitative differences. First of all, the classic effect is linear. The liquid crystal effect is strongly nonlinear, mainly quadratic in the applied field. That means that you can apply not only DC field, but also AC field to drive it. You don't have problems such as blocking of electrodes. You can create steady flows. As long as you have the field and change its polarity, the flows will be persistent. You don't need any properties of the particles to have them transported. For example, you don't need them to carry any surface charges. The particle can be a droplet of water. You can still translate it. The particle can be even a bubble of gas. You can still move it around. So it looks like there are many opportunities with this approach to use liquid crystals as electrolytes. With this, how much time do you have?
We started late.
Okay. So the second part is shorter than the first one. I would like to ask you, when you see this picture, what kind of associations come to your mind? Anyone? Isotopic pneumatic.
Polar pneumatic.
Polar pneumatic. Good.
Can't be a pneumatic because it's got arrows on it.
Okay, now the only thing I change, instead of M or N, I put V. Any other ideas?
Flocking.
Flocking, exactly. So this is an example of the active matter, more precisely the Vissek model of active matter. So Vissek predicted that if you have moving objects and increase the density of these moving objects, or increase their velocity, sooner or later you would have a phase transition even in two-dimensional model, in the sense that uncorrelated movers would start to move in the same direction. So it's very similar to the isotopic to pneumatic phase transition, but it's in a totally different realm of physics. It's moving objects that by themselves might not be necessarily very elongated, etc. So over last 2 decades, people developed experimental models of active matter. One of the first was Ramaswamy's model of jumping rods. So he would create metallic rods and then vibrate the substrate, and they would form this pneumatic order with disconnections. More recently, Oleg and his colleagues developed more biologically inspired system with microtubules powered by micromotors that show local pneumatic order and topological turbulence of defects. So in active matter, we have 2 things. We have activity, that is basically presence of a velocity field at each and every point in space. And very often you have this orientational order that at least preserved locally. So we decided that maybe liquid crystals can offer something in addition to those models. And what we decided to propose was the so-called living liquid crystals. So living liquid crystals represent a dispersion of a liquid crystal that is just normal liquid crystal that is uniform if you align it and keep it in equilibrium conditions. The only difference is that this liquid crystal is of lyotropic origin. It is based on water solutions of organic molecules. And so in this liquid crystal, we disperse bacteria. Rod-like bacteria, Bacillus subtilis, that have the shape of rods and have the flagellum, the helicoidal thing that rotates and propels the bacteria. So our idea was that with this system, we have independent handles of control over the orientational order. We can switch it on or off by changing the temperature. And also, we can change the activity of the bacteria. For example, if you deprive them of oxygen, they would go to sleep. But then if you give them some oxygen again, they would start swimming. So this is one of the typical examples of how the system behaves. The Lake crystal is uniformly aligned, and you see that these rod-like bacteria swim, but now they are swim in a single direction. You remember the tumbling movie from the yesterday talk where the bacteria would go into different directions. Here they could not. They just swim parallel to the director. If the director is distorted, and these distortions here are created by isotropic inclusions of the matter in near the phase transition, you might see that the bacteria follow the director field rather precisely, and then they go around the inclusion and escape. So by patterning the director field, you can control the direction of the bacteria. This anisotropy of the Lake crystal also creates an interesting and potentially useful effect. You can force the bacteria to bring your cargo from point A to point B. The red arrow shows the fluorescent particle that sits here and waits till the bacterium shows up and propels it to the right-hand side. The bacterium cannot escape to the right or to the left to go around this obstacle, and it simply pushes it forward, and thus it's the cargo effect. The yellow thing here shows the particle that is slightly below the projected trajectory of the bacterium, and you might see that the hydrodynamic interactions are very weak in this case, and this particle is not painful. So by placing the bacteria in the Lake crystal, you'll learn a little bit more about the bacteria themselves. For example, birefringence of the Lake crystal, in other words, optical anisotropy, allows you relatively easy to measure the frequency with which the flagellum rotates and the frequency with which the head rotates. And here you see an example that shows that the two rotate with frequencies that are in the ratio of about 7. So that was just the preliminary study to understand how individual bacteria behave in the Lake crystal. But our main interest was to explore how this activity in the continuum limit would make the difference and bring the normal equilibrium uniform Lake crystal into the non-equilibrium state. So what we did, we dispersed the bacteria, and at first we deprived them of oxygen so the bacteria wouldn't swim, and you see them being aligned perfectly parallel to the director of the uniform Lake crystal. Then you switch on the flow of oxygen, and the bacteria start to swim up and down, but simultaneously with that activity, you see a dramatic change in the director field. The director field is not vertically uniformly aligned anymore. It shows this bending with a characteristic period. This period would decrease as the amount of oxygen is increased, and if you move from the right-hand side to the left-hand side, this is how the oxygen is increased, and you might see that this period is shrinking. The next slide shows the movie of the oxygen being supplied from the left-hand side, and you see the development of this striping that destroys the uniformly aligned director. So the mechanism of this thing is relatively simple. What happens is that when the bacterium swims, it has two jets of water being expelled from the head and from the tail. And whenever you have this in the anisotropic environment, and whenever there is a fluctuating tilt of the bacterium, then this tilt creates a shear in the horizontal direction, and this shear wants to realign the director as shown on the right-hand side. And this is the reason for bending, but of course the Lake crystal is elastic medium, and any deformations are resisted by the elasticity of the director. And if you balance the hydrodynamic force that wants the director to be bent with the elastic stabilizing force, you get the expression for the period psi, and as you see it here, this period would become smaller as the activity is increased. The activity is in the denominator. So with this, you can increase the amount of oxygen further, and then at some point you see a topological transition from this more or less nicely shaped band stripe pattern into the pattern of moving disclinations. So the band deformations are replaced by splay and band deformations, and the system starts to show constantly changing director with disclinations of +1 and -1 type. So thus we conclude that when you increase the activity of the actively crystal from 0 to some maximum value, you go through a cascade of instabilities. The first one is the banded instability with formation of periodic stripes, and then at higher levels of activity you have the formation of topological turbulence with disclinations nucleating and perturbing the director field. So our conclusion number 2 is that living crystals represent an interesting fundamental model for active matter, and who knows, maybe one day we will find practical applications in bacteria as the working force. And to summarize the entire talk, I would like to stress that living crystals are not only the material of choice for informational displays. If we try to see what they offer in other areas, we might find that there are some interesting potential that is unexplored, and most probably that new areas will bring some new applications. This work was would be impossible to do because it was done mainly by the students. The names Israel Lazo, Chen Kuikan, Taras Turiv, Sean Zhu, Sergei Chernovsky, and Chico Wei, and his students are helping us in the current project. Tony Yakle was at the beginning when he started with him the exploration of some dynamics in colloidal systems. And the part on bacteria was done in collaboration with Argonne National Lab, Igor Aronson, and Jason Kuhl. Thank you very much for your attention.
Oleg, very nice talk. Just a quick question about this surface, this anchoring strength, because there, because you know that the technique is dependent, right?
Elsie, can you use the mic? Right behind you.
So what's the, so the question is, what is the maximum volumes that you can have, the limits of the volume that you can have still maintain that laminar flow or the director fields of the bacteria, either the bacteria or the particles?
So 100 micrometers would be the ballpark estimate.
Say that again.
100 micrometers.
Okay, I have another question in the back.
So, thank you for the talk. You mentioned something about the orientation. I mean, when you have charges in the nematic liquid crystal, they're moving along the director. What happened to the column force? Because I didn't expect that all positive charge just line up in one layer. I expect that when there's a positive charge there, the negative is going that direction.
No, of course, the picture is not as simple as this one. The main point is to state that the accumulated charges are proportional to the electric field that drives them, but it doesn't mean that all the charges would have time and desire to go into this crowded environment of similarly charged entities there. So, it's not a statement that all the charges go into the same places.
Any other questions? I wanted to ask, just a second. There, historically, I think I mentioned to you before, J.D. Burnell put a goldfish and a seahorse into a lytropic liquid crystal. Do you have any idea of doing something larger than just tiny bacteria? He did that, I don't know what,
You know, time to time I go to have lunch at the student center and I pass through the biology department and I often see threats written on the sidewalk by people caring about animals. So
The goldfish and the seahorse were not harmed in the experiment. They used tobacco mosaic virus.
so yeah, it's a good question, but so far we are dealing with small ones.
Only bacteria. Okay, were there any other questions? Elsie, have another question.
So in your electrophoresis, right, there's factors of viscosity. So the isotopic media and your pneumatic media are quite different. So what happens with the KBT increase in terms of this effect of those two parameters in isotopic and pneumatic?
So yes, there are differences. In the case of colloidal electrophoresis, the viscosities are maybe 3 times different, the relevant viscosity. So we see some drop in the velocities, but the gain that instead of just DC moment and no displacement when you apply AC field in the isotopic fluid, when you see this unidirectional motion in the liquid crystal, the gain is enormous. So we are happy that it's a qualitatively different phenomenon, and yeah, we will be glad to pay a price in terms of 2-fold or 3-fold decrease in the velocity. What is more interesting that I didn't have time to explore is that the bacteria. Turns out that the velocity of bacteria in the isotopic fluid and then in the pneumatic of the same material are only by some 40% different. So despite the fact that in this biotropic medium that we place them in, the viscosity of director distortions is 1,000 times higher than the viscosity, shear viscosity of the isotope. And this is really amazing. And it is related to the very fact that bacterial motion is not that much dependent on the overall viscosity of the medium. It is powered by the anisotropy of viscous stress in the direction parallel to the piece of flagellum and perpendicular to it. So it turns out that in liquid crystal, despite the fact that the whole general viscosity is much higher, this anisotropy is preserved, and this is what propels the particles, and this is why the velocities are the same.
Sister.
This is a question from my bias in applied science. Could you use it to do electrophoresis of molecules, DNA, proteins? Would it have an advantage over polymer gels?
So we might think about this, especially in the realm of this picture of the crystal-enabled electroosmosis. In principle, that's exactly what we are trying to explore right now. How are we going to apply this to, let's say, separate particles of different properties? So this work is relatively new. It's 2015, so we cannot answer much about practical applications simply because it's early.
But for instance, if Chiho wrote a pattern that was not many parallel roads, but one road on a background, you could actually make a pathway for particles to follow or for flow to pursue. So that that capability of localizing flow seems promising from the point of view of microfluidics as an alternative to glass walls to have patterned substrates.
Yes.
Any other questions? If not, let's thank Oleg for a beautiful talk.